Good afternoon, everyone. I hope you are all ready for doing the laboratory test, and we'll start in 10 minutes, okay? Before we need to talk a little bit about the theory that we need in order to understand what we're going to do. So far we have talked about stresses, and we have talked about strains. Today we're going to find the link between those two, between stresses and strains. And those go for the general name of constitutive relationships. And basically what we want to know is, for example, if I give you a given stress, and that's the input, I'd like to know what is the output, what is the strain. And in the same way, if I gave you a given strain, I'd like to know what is the output, what is the stress. And what we're going to see today is the most basic constitutive relationship in mechanics, which is linear elasticity. Linear elasticity, probably you remember this related to Hooke's law, right? Can anyone tell me what is Hooke's law? In one dimension.
The force is proportional to the essential spring.
To the spring, right? And if you put it in terms of stress and strains, Hooke's law will tell you that stress is proportional to strain through one parameter, which is the Young modulus. This is in one dimension. But our job now is going to be to extend this and generalize this Hooke's law to 3 dimensions. And it's going to get a little bit more complicated. Now I'm not just going to have one number. Remember, I'm going to have a matrix here, and it's not going to be a number. This is going to be a matrix, and this thing in between is going to be a matrix too. But let's go step by step. As we always do, we're going to put a coordinate system 1, 2, 3, and for that coordinate system, I'm going to have a solid. It's going to be a prismatic element in which I will apply stresses on the top surface that if they are, can you tell me what is going to be the name of this stress according to what we have seen so far? It's going to be sigma what? What?
3, 3.
Sigma 3, 3, very well, because it is on phase 3 and it goes in direction 3. This is sigma 3, 3. Okay, I'm going to apply stress on one side, and this other side, I'm not going to let it move. Those triangles means that it's not moving in direction 3, but it's on rollers, so it can move in directions 1 and 2. This will be very similar to this piece of rubber that I have over here. And if I apply stress in this direction, it shortens in direction 3. And I don't know if you can notice or not, but it's getting also a little bit larger in directions 1 and 2. Probably if I it's really harder, you will see that it's getting larger in direction 1 and 2. So if we draw what happened here, so with these dashed lines, we're going to draw the deformed shape of the solid, and it's going to be something like this. It gets shorter in direction 3. So, for example, that move a distance du3. The original length of the solid, let's call it dx3. If you remember from what we talked about strains and deformation, the deformation, linear deformation in direction 3 is going to be the change of length divided the original length. And by analogy with Hooke's law for one dimension, I'm going to say that the strain that I cause here is going to be proportional. It's the same equation as this one in the top. It's going to be proportional to the value of the stress applied on that phase. And it's going to be inversely proportional to the Young modulus. And in this case, I'm going to go a little bit further. This is called linear elasticity, but it's also isotropic. That means that it's the same in all directions. Okay, so from here, I already have what is the Young modulus. If I wanted to measure the Young modulus, basically I will have to measure a change of strain divided a change of stress. And we'll see why we need this delta here, but you will see that it makes a lot of sense just in a bit. So the Young modulus is going to be, there's a mistake in my equation. Sigma goes on top, epsilon goes on the bottom. Oh, by the way, talking about mistakes, you know, at least to me it's quite hard to speak one thing and write another thing. So I found that I had some mistakes in my matrix last time. This is the right one. So just, you know, when you check the videos again, make sure this should be D1, X1, D2, X2, D3, X3. And here, 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. Okay? All right. So, the Young modulus is going to be the difference in stress divided the difference in strength. And you know how I noticed I had a mistake? I saw the equation right away, and I noticed there was a problem with something that also you should pay attention to. I saw there was a problem with units. What are the units of a Young modulus according to this equation? What are the units of strains? Strains are displacement or length divided by length. So no units. And what are the units of stress? Pressure, let's say in general. So the units of the Young modulus are going to be pressure too. So force divided length squared. It's the unit of the pressure. Okay. The Young modulus is going to tell you how hard the material is. And if I remember correctly, I have some examples in my notes, typical values of the Young modulus. And here. go somewhere else. Okay, well, I don't have it as a table, but typical values of Young modulus of a rock will go all the way from about 1 gigapascal to more or less 50 gigapascals. And in terms of PSI, this is equivalent to about less than 1 million PSI. I'm not going to use the field units because that causes a lot of trouble all the time. So let me just do this. From about 10 million PSI or less than that to a maximum of like a few million PSI. So let's say here 7 million PSI. And because of that, some of these strains are very small. When you divide the stresses that we deal with in real problems, which are in the order of 1,000 psi, divided 1,000,000 psi, gives you strains in the order of 1,000. So which is very small. And sometimes, when we run the test today, you will see that you are not going to be able to see like the deformation. In this case, this is very soft, so you can see how it deforms. But with the rock, it's so stiff that you will not see any deformation, but we'll be able to measure it with some devices that we have. Okay, Young modulus. It tells you how stiff the rock is. The other quantity that we're going to measure today is what is called the Poisson ratio. And the Poisson ratio by definition is going to be, and it's going to quantify the amount of lateral displacement, or how wider it gets the sample in, let's say, in direction 1, divided, actually, we're going to change it to directly to strains. So remember, this was strain direction 3. The same way, the change of displacement in direction 1 divided the original length in direction 1 is going to give me a strain in direction 1 divided the strain in direction 3, always for this type of test in which I apply stress in one direction and I let it expand in the other direction. Okay, so from this figure we see that epsilon 3,3 is a shortening, is a contraction, right? What about epsilon 1,1 in this direction? It's an expansion, right? And because it's an expansion in geomechanics, we're going to say that that's a negative quantity. So when we actually measure this value, it's going to be negative. We don't want to have negative coefficients. And that's why here we add a negative sign. And the value of the Poisson ratio is going to be negative the ratio between the strain in perpendicular direction to the load divided the strain in parallel direction to the load for this type of test, which is axial loading with no, or we're going to see later on, which is the same to say constant confinement. And in general, we're going to see that for real rocks, we're going to have to do something similar to what we did over here. We're going to have to deal with changes of strength rather than absolute strength. Do you remember what are typical values of the Poisson ratio?
Point two.
0.2 is a typical value. For rocks in general, it goes from 0.1 to more or less 0.4. What is the maximum value of the Poisson ratio? This is a question I like to take in exams. 0.5. Why?
So the volume is.
The maximum value is 0.5 because if it were to be more than 0.5, that would mean that you apply strain in this direction and it has a strain which is larger in the other two. And that doesn't make a lot of sense because that means that you apply a compression and everything expands. Or the volume actually dilates, which that's something that does not happen with most solids. Okay. This is the theory. Let's say now what is the practice when we measure actually these Young modulus. Okay, so we're going to do this experiment now. And now I'm saving you 2 hours of your week because we're going to do this in half an hour here. We're going to get a rock sample that is cylindrical. I'll tell you what is the length and I'll tell you what is the diameter. Okay? And we'll apply a force on it. As a result of that force, and here I'm going to plot force divided by area, I'm going to plot the strength in axial direction, which is along this axis will be the same as